was only a very small subset of the components in the model and only a very small subset of the sequence positions in this model, in the like forward pass of this model for these particular type of sentences, were actually being used for like a relevant and important computation. And so you can like ditch the rest of it, and the model like kind of delete those components. The model still works perfectly fine. And so this is like a really good way of what the circuit is doing. And what's especially interesting about this technique is that they actually kind of looked at techniques that they used to find the circuit and said, okay, how can like figure out without having to go through all this like manual by hand analysis what the circuit is. And so they developed this method called ACDC, which stands for Automated Circuit Discovery, which basically involves starting with a fully connected graph of all of the like model components and kind of snipping edges from this graph. In other words, like kind of deleting the values that like certain components produce as output until you're left with this like very minimal circuit that ideally looks something like this, and that like shows you exactly which components are important and why. Well, not necessarily and why, because the and why often like requires like a different type of reasoning, but it's a really good start for analyzing a circuit. So yeah, to recap this, some high-level ideas: finding circuits to explain model behavior. In other words, like trying to find a small set of components which link up together. In other words, the output of some component is important for the input of some other component. And collectively, these components like all produce the output that we can see, which in this case is like the model choosing Mary over John. Causal interventions, in other words, basically like figuring out whether a component is important by changing its output, like manually changing its output during a forward pass and seeing how the output of the final model changes. And then another key idea here is automating interpretability. In other words, like seeing which techniques worked well in this case and like trying to scale it to much larger models so that you don't have to do everything by hand. Cool. So second case study, there are 4 case studies in total, by the way. Yeah, second case study, OthelloGPT. Basically, some researchers took a transformer which had been trained to predict legal moves in a game of Othello, and they tried to discover whether the transformer had some kind of like internal world state. What I mean by that is the task of predicting next moves in the Othello game is actually non-trivial because it requires you to have kept track of all of the like moves and captures that have happened up until this point, because like a particular move might flip some of your opponent's pieces to your own color. And in order to figure out which moves are legal, you have to keep track of the sequence of moves that have been played and like the basically the captures that have been taken. And so what these researchers were trying to figure out is like, is there some kind of like representation of a board state that the model creates from its from the input sequence, and then it uses that board state to like extrapolate what the actual legal moves are. And they try to use linear probes to find this. Linear probes basically like you train them on the internal activations of a model, and they're going to look for directions in the space that you're training on that you can just like project vectors in that space onto, and the value of that projection will tell you whether this thing is like true or not. So in this case, they were like looking for a particular vector in the residual stream where like projecting onto it would tell you if this square was white or black or whatever. And unfortunately, they didn't find that. And this is like kind of a blow for interpretability if these kind of representations don't exist. But what Neil did to basically like build on this work was try and use a different abstraction. In other words, not thinking about the pieces in terms of like black and white, but thinking about the pieces in terms of mine and theirs, where mine is like the piece that is the same color as like the position in the sequence of moves that we're currently looking at, and then theirs being like the opposite color. And it turns out that you can get linear probes working when you do this. And the reason that you couldn't get linear probes working if you just looked at like black versus white is that essentially you were having to learn a parity operation to flip the like odd colored results to be like the same equivalent to the even colored results. And like a parity operation is not linear, so the probes are like unable to learn this. And yeah, this is pretty interesting because it's like, I mean, firstly, it's a point in favor of the linear representation hypothesis, which basically says that like most things that you might want to know about a neural network are probably going to be represented linearly inside that network's activations. And like another key point here is that this was about finding the right abstractions, because the reason that the initial linear probe study failed is because it was like assuming that the model's abstractions were like black versus white pieces, but actually it turned out to be mine versus theirs. Yeah, and then this is just sort of like illustrating the point that I was saying that like the initial theory was maybe there is no board there is no like model of the board state, and so this this transformer is just learning some kind of like shallow lookup table involving like a bunch of heuristics, which would map from previous moves just to like directly predicting the next legal moves. Kind of board world model that's basically an intermediate step in that causal pathway. And one of the ways that they showed this was by performing causal interventions on this world model and showing that like you can take the directions that were found by your linear probe and intervene in the forward path along those directions, and you can cause the model to have different predictions in a way that is according to what your understanding of the linear probe would predict. So you can like make a model think that a particular square is white and black, and so that causes them to have like a different guess at what the legal moves are that is like in with new board this new board that it's seeing. And this is like pretty important from also from the perspective of much larger models, because obviously it's a very different situation. But one of the main debates around models like GPT is, do they actually have what we would like coherently describe as a world model, or are they just some kind of like shallow like collection of heuristics? And this kind of evidence shows even in a very simple case, it's like advantageous for the model to have some kind of like representation of the board, and it to use that to extrapolate its predictions from. So yeah, to recap that, some key ideas: identifying the model's abstractions and not just like trying to, not just like assuming that you already know the right abstractions coming in. Finding evidence with world models. This is one like really interesting thing that this work did. And again, we have this idea of like causal interventions, basically of having a hypothesis about the model how the model works, and validating that hypothesis by changing the altering the model in some particular way during a forward pass and seeing how the output correspondingly changes. Cool. Third case study, steering vectors. There's a bunch of like related work on steering vectors, and I think a lot of overlaps. Like some of the earliest work on steering vectors was basically by I think Tantrout and basically the like Alex Turner's team like a few years ago, and then also there's some like work by the Bao Labs on it related to like function vectors. So like a lot of different angles people take in the world of like steering vector related techniques. But broadly speaking, the idea behind steering vectors is that you take you like find a vector using some method which corresponds to like some particular concept or like some particular feature. You intervene during a forward pass by like adding that vector into the model's activations, or like changing the model's activations to that vector, and you get the output to produce more of this particular thing that you think the steering vector corresponds to. So here's just like an illustration of this in a generative model which produces like celebrity pictures. These people like found a steering vector that corresponds to like the concept of smiling, and by adding progressively larger multiples of that steering vector, you can just like edit the model's output and have it produce a picture which is smiling. And yeah, so one of the particular ways that you can do this is by taking sentences that have like a contrast pair. So for instance, like I love you because and I hate you because, and getting the difference between the like model's internal activations in these two sentences, and then kind of like using that vector to add during a forward pass in an unrelated prompt, and like inducing a particular behavioral change. So here, like if you take the love minus hate vector and you intervene on it in this forward pass, then you can make the model complete the sentence like I hate you because with something that is in correspondence with the the love concept minus the hate concept. In other words, it's like completing the sentence in a way that you wouldn't otherwise have expected. If anyone's seen the like Golden Gate Claude work that came out of Anthropic a while ago, this is a similar idea, and actually I will get to that in the fourth case study. But yeah, essentially they're like inducing this particular behavioral change from this adding this vector. The thing about like steering vectors is it's not strictly mechanistic interpretability, because although it might help you understand better like how the model uses these particular steering vectors and like what the causal path the model uses is, they are not themselves a mechanistic interpretation of like, and so it can be important when you're like studying steering vectors, if you're trying to do mechanistic interpretability, to make sure that you're not basically like drawing hypotheses that are too strong based on the evidence you're actually seeing. You don't want to assume something that's like not necessarily true. But yeah, so some key ideas: steering vectors ability to like again, we have this idea of like causal interventions coming up where you can like take a steering vector and patch into the model's internal activations during a forward pass, and you can like change the model's behavior in a certain way. And yeah, even though like steering vectors aren't strictly mechanistic interpretability, it's definitely the case that understanding mechanistic interpretability better can cause you to maybe like create better or like more effective steering vectors, or better understand how steering vectors work. And it's like pretty, you can imagine that this kind of technique of using steering vectors could be pretty useful when it comes to like suppressing harmful behavior, or like trying to make models behave in a particular way that we interesting steering vectors that you found that bring about interesting behavioral changes. So actually, I worked on the scaling monosemanticity paper in when I was at Anthropic, and was able to sort of work with that team while they were producing these results and sort of demoing all of these like steering vectors. Actually, section is on SAEs, but I think like the especially interesting thing about steering vectors when you get to that scale is that you can find vectors that not only correspond to like very low level concepts that can be described by a single word, but like very high level abstract concepts that actually induce like very complicated forms of behavioral change. So yeah, I'll discuss that when we get to like Golden Gate Claude. Cool. Yeah. Final case study, fourth one, dictionary learning and sparsal to encoders. Again, I'm not going to get like too in depth on exactly what sparsal to encoders are because it's like quite a like deep technical topic. But in to summarize the broad strokes, sparsal to encoders are basically one of the most interesting areas in mechanistic interpretability right now. They essentially find things that you can use as steering vectors, but rather than finding them in a supervised way by like taking a batch of inputs that represent some concept and then taking a batch of inputs that represent its opposite and taking the difference in those activations. They actually find these concepts in an unsupervised way. They are based on a theory called the theory of superposition, which basically says that models need to represent more concepts than they have the capacity to represent. And so what they do is they cram all of these concepts into a much smaller space. And there are some like clever mathematical techniques that it can use to like cram all these concepts into a smaller space. In particular, the fact that these concepts are sparse, meaning like most of the time they won't come up in any given text. Like any given piece of text isn't like if you come up with some concepts like the Golden Gate Bridge or long division in mathematical equations, these concepts are going to be pretty sparse because they're not going to appear in the average like bit of text that you select at random from the internet. And so because these like features are sparse, you can essentially like cram all these features down and store them in a smaller space. And by kind of like what sparsal to encoders do is they basically learn a mapping from the model's internal activations to this hypothetical larger space of all the features that the model represents. And there's been some really interesting results in SAEs that have come out over the last few years, especially from Anthropic, but also from DeepMind as well. This sort of illustration here basically explains sparsal to encoders. But like maybe if the model's internal activations are this kind of like very compressed down version of the like full feature space, then it's really difficult to interpret any given activation. But what you want to do, and what SAEs allow you to do, is basically learn this much larger, like unfolded version of the original set of activations, where yes, there are more neurons to deal with, but any single neuron only fires very, very sparsely, and it's often going to be more interpretable. And so you can actually expect a single neuron to correspond to a single feature of the underlying data. And yeah, that's basically what you get from SAEs. If anyone's interested in like reading more about this, I think the first paper I'd recommend is Anthropic's Towards Monosemanticity paper, which came out last year, and basically shows how you can train a sparsal to encoder on a simple one-layer transformer and extract the vast majority of like useful interpretable features from this transformer. It's very interesting. Yeah, the work in sparsal to encoders has definitely come a long way since then. One of the things that we can do is train sparsal to encoders very, very large models and extract high-level concepts. So what happened here was the researchers at Anthropic trained a sparse autoencoder on a very large model and found a feature that corresponded to the Golden Gate Bridge, by which I mean that feature was strongly active whenever the Golden Gate Bridge was being discussed in the underlying text that was being fed to the model. And it turns out that by like artificially feature strongly, you can actually like induce this behavioral change by making the model like talk about the Golden Gate Bridge in a super unprompted way, which is kind of what it's doing now. There are a bunch of like viral things that were like pretty funny if you go back to the internet forums during that time. And yeah, to like follow up on the stuff I was mentioning earlier, if you read the scaling model, the niche features that were able to be found that represent these like highly abstract concepts, but still have these very powerful like behavioral changes when you actually scale on them. Like I think there's a whole section of the paper that discusses potentially harmful features and like for instance, at the very start, there's a feature that like a demonstration of a feature that causes the model to be more sycophantic. And so it's not just going to like repeat the word sycophantic over and over again or something, or like talk about sycophancy abstractly. It's actually going to demonstrate sycophancy by telling you all your ideas are great and you're like really really smart and this kind of stuff. And I think it's just very interesting that we're able to take a technique that's fundamentally unsupervised. So like we're not looking for these particular features. We're just looking for a mapping from a smaller activation space to a larger activation space with the assumption that that larger space is sparse. And then the things that we are finding happen to be really interpretable and like very steerable and able to induce these like complex forms of behavior. Yeah, and there's like a lot of really, really interesting work being done by SAEs, which I don't have time to get into in this talk because I know we've just got 5 minutes left. Like for instance, work on circuits is really, really interesting. To connect it back to the circuit, the indirect object identification circuit I was discussing at the start of this talk. It would be really promising if we could find circuits involving features in sparse autoencoders, and like ideally we would what we would find is that those circuits are a lot more sparse and more interpretable than circuits that involve just like model components. In the same way that individual SAE features you might find to be like more interpretable than like neurons in an NLP layer. Okay, so yeah, to review the key ideas for dictionary learning SAEs. Yeah, resolving superposition. Superposition, this idea that you can cram a bunch of features into a smaller space of activations. Features. Picking the right ontology. This idea came up again in Golden Gate Claude, but we basically have the idea that, like, for instance, in an MLP layer, the neurons aren't the right ontology because of superposition, but maybe the features found by sparse autoencoders are the right ontology, and they actually, like, in a meaningful sense, represent the units of computation that your model actually uses. And then, yeah, finally, causal interventions based on understanding your internals. I feel like this come up in all 4, but that's because it's a really important idea. Okay, yeah, and then this is just a recap of all the 4 ideas. There are a few more slides related to that I've included here related to a discussion of like theories of change. I don't think it's worth like diving too deep into them because this is like a hackathon talk, and I'm sure that the majority of people here are interested in just like interesting projects to work on and getting an idea of mechanistic interpretability. But yeah, for anyone who is like the arena material, I can share my slides after this. Yeah, reading the arena material, reading things like sections of the AGI Safety Fundamentals program, which I think definitely motivates why interpretability is a really valuable tool to help us reduce the threat that advanced AI systems might pose. Yeah, I think to kind of like discuss one framing presented in the slide as to why I think that interpretability, a whole like alignment story, I think that interpretability goes about trying to reduce risk from advanced AI systems in a way that's like not necessarily as emphasized in sort of community, the existential safety communities, by kind of like forward chaining from the questions that we don't know how to understand right now, questions about like exactly what kind of risks that AI models are going to pose into the future. Not that it's not valuable to ask those kinds of questions, but I think like often the way that a new science progresses, especially when there's a lot of like uncertainty about it and disagreement about what fundamental concepts mean, the way that science progresses will be by starting from the situations where we don't really understand like how something works and trying to build off it and like fix the problems that are in front of us right now and like see how far we can go from those solutions. Cool. So yeah, I think that's pretty much the end of my talk now. I will questions. Is there a hard cut off at 1:30 that I'll have to abide by? Yeah, sounds good. So yeah, can you generally operate in steering vectors to compose steering? So actually, David Bau's function vectors and paper does discuss this a little bit. Essentially, you can perform um, something like steering vector arithmetic using steering vectors. Vector arithmetic is this kind of like thing that helps you understand the latent space that you're dealing with slightly better. Like for instance, in certain latent spaces, if you have a vector that corresponds to like king and queen, then you can take the difference between those two vectors, and that will often be like a vector that encodes some kind to kind of get the male or female version of those. And that like helps you understand the latent space a bit better, and also helps you understand the like sort of biases and like viewpoints that your model kind of like implicitly holds via the way it's representing things. And you can do somewhat similar things as steering vectors. And I think like the Bao paper explores this idea of adding together steering vectors in two different tasks to induce kind of like behavior to solve the composite of those two tasks. Like, you know, for instance, the if you add the task vector for translation to French with the task vector for like the creating the opposite, like producing the opposite word, then you might hope that the model is induced to solve the task of translate the word into French and then find its antonym. And it kind of does do that. There's like exactly how successful it is sort of varies. And yeah, this function vector in large language models is the paper that I was discussing. Yeah, like how effective this varies, but this is a thing that you can do. Yeah. But again, like it's the kind of thing that you can empirically test, but also it's worth um, and this is a theme in a lot of mechanistic interpretability. It's also worth thinking about what aspects of the structure of underlying data might cause this to be true, or might cause this to be useful. Like a useful way for the model to represent things. Because often the reason that vector arithmetic works is because the vectors corresponding to any given word have been like trained in a way that makes this kind of vector arithmetic helpful. And that's not always going to be the case when you're dealing with some kind of like internal activation of a model. Why does it make sense for models to want to represent things linearly? Is it less inference? Yeah, so this is a really interesting question, and to there are like quite a few different reasons you could discuss, but to basically summarize it, um, in lots of different types of neural network, and especially in transformer language models, the reason it's useful to represent things linearly is because you can think about transformers as having a central object, which is the residual stream, and every component in the transformer like either reads from or writes to the residual stream. In other words, they like take in the input, they take in the current value of the residual stream as input, they do some computation, and then they add the output back into the residual stream. And both processes of like taking the input and taking the output start with a linear projection. So it's really, really helpful for the model to actually have these things represented linearly because like so much of the way that the model deals with that information is inherently linear. And so like it doesn't get much, you don't get much advantage from representing it in some like more complex way because the model would have to devote like extra capacity to like dealing with it and kind of unwrapping the nonlinear representations to actually like get at the linear ones. That being said, like how much people sort of buy the linear representation hypothesis will definitely vary depending sort of like of the last year or so that discuss like high level geometric representations that might exist in the residual stream that aren't necessarily purely linear. I think there was a recent less long post called something like, actually this one wasn't as recent, but it's called something like superposition, like feature geometry is outside the superposition hypothesis. I'll just like add that text in. I think if you Google it, you'll be able to find it. But yeah, I would recommend like reading that. I think that gives like a lot of good ideas. Right. I No problem. Yeah. To very just quickly fire off. Oh, yeah, that's the one. To quickly fire off answers to those last two questions. Is the interp work happening for non-transform architectures like Mamba? Kind of yes, but less than would be ideal. I think there was a group work that I saw working on Mamba in like Eleuthera AI or something a while ago. I think there's like definitely people who are interested in that if you sort of scope around for it. But yeah, definitely like we don't know enough about that as we should. Have we found any examples of nonlinear structures? Somewhat, but it's like for instance, you can show that like days of the week are represented in some kind of like circular way, but this is sort of a kind of linear representation. It's just like linear in 2 dimensions rather than one. In terms of like higher than this number of dimensions, no specific ideas are like jumping to my head, but like I'm sure there are people who have sort of done research on them. And yeah, would definitely recommend reading the feature geometry post. Yeah, so thanks everyone. I really appreciate it. And yeah, so feel free actually a link to the arena material if anyone wants to have a look at it. And there's also a link to the Slack channel there as well. So feel free to use that link to join the channel and reach out to me if you have anything you'd like to ask. Awesome, great, thanks. And yeah, I would recommend, by the way, for anyone who's still on here to definitely go to Joseph's talk. I think that's probably going to be really good. Yeah. Great.